So let's continue from the point where we left the previous time. This point was the interpretation of the universal constant pi, which characterizes our areas on the geometric domain in terms of synchronization that takes place in the harmonic domain. Recall that the harmonic domain is a domain pertaining to wholes, to global entities. There is no local global or part-whole relation in this domain. So everything is a whole, and this whole with different frequencies, they enter together into synchronization in what we have called symphony cycles. The domain of geometry is the domain of the part-whole or local global relation. And in this domain, the basic equation pertaining to areas is given by the Pythagorean theorem. So our spectrum in geometry is always a Pythagorean spectrum of areas. Now we want to see what this tuning amounts to. How are we tuning such that we get the chromatic scale, so the equally or well-tempered canon, if we think in terms of music, for example, but pertaining to the whole domain of harmonics, so irrespectively of sound, in the quantum space, how this tuning takes place. This is a way of interpreting, in terms of natural communication, of the fundamental theorem of algebra. So the theorem that we prove is that the tuning, the universal tuning, according to the constant pi, to the real constant pi, takes place according to the fundamental theorem of algebra. Recall that the fundamental theorem of algebra says that every complex polynomial, so a polynomial of a complex variable where the coefficients are complex coefficients of the nth degree, has precisely n complex roots as solutions of this equation. And in this way, the complex number field is an algebraically closed field. So any polynomial equation has roots in this domain. So the fundamental theorem of algebra, together, of course, with the universal equation of ciphers, is what characterizes our tuning by the real transcendental parameter pi, pertaining to areas geometrically. So we consider the notion which is called the roots of unity. This is the key notion in order to make sense how this tuning takes place. Now, what are roots? Recall that roots are solutions of polynomial equations. The simplest type of these polynomial equations is that if I consider a complex number z, to the power n equals the unity. So this is the simplest form of this polynomial equation. The roots, so the solutions of this equation, which if the polynomial is of the nth degree will be n. So if I have 5 as a degree of polynomial, I will get precisely 5 roots. In the case of this simplest polynomial equation, which says that the power of a complex number equals the unity, gives rise to what is called the roots of unity. The roots of unity now give us the way that the tuning by this parameter pi, this constant pi, which is real, takes place, so that harmonics and geometry are in natural communication to each other. So I consider as an example the notion of the 8 roots of unity. What this says? That imagine a complex number w to the 8th power equals the unity. So if I bring the unity to the other side of the equation, I have w to the 8th power minus 1 equals 0. This is an equivalent form of this equation. The complex number w which satisfies this equation, so the solution of this polynomial equation, are called the roots of unity. So basically, how we grasp a root as a solution of an equation of this form, of this algebraic form, is what neutralizes a power. So, the synthesis of a root with a power gives rise to the unity, which is expressed by the 1 in the domain of the field of complex numbers. Now what this shows is that, recall that the unity in the complex plane should be thought, as we have explained a few lectures ago, in terms of the unit circle on the complex plane, so on our screen. So the roots of unity are solutions of an equation. What they show is how our tempering in terms of the tuning parameter pi pertaining to geometric areas is distributed uniformly around the unit circle on the complex domain. This is how we will understand the roots of unity. So, by the fundamental theorem of algebra, since we have an equation of the 8th degree, there will be precisely 8 roots, so 8 points on the circle, or 8 faces on the circle, which are distributed uniformly around the center of the circle. So, in this way, with the roots of the unity, we get an objective probability distribution which uniformly distributes around the center about which we think of a center of synchronization, the undisclosed geometrically notion of synchronization, the role of the center. So, in the case of the polynomial equation of the 8th degree, we get 8 roots, which you can see here, W1, W2, W3, up to W8, which of course is the unity root. You can see pictorially that all these roots are uniformly distributed around the unit circle. Now let's think what the sum of these roots of unity gives. We can give a very simple argument, since we know that in the complex plane, the center of the unit circle is a center of synchronization. So it's not a geometric origin of a geometric circle, because we have the complex structure given by the imaginary unit. Now, if you take the sum of all these roots, think of each root as a vector, which will be, in our setting, a velocity. So here we have a synchronization of all the velocities harmonically parallel transported to the center. So each one of them from the center will correspond to a vector. And the tip of this vector points to a face which is a root of unity as a solution of the corresponding polynomial equation. Now, if you take the sum of all these vectors, so you consider the average, you see that they cancel out. So the sum of all the roots of unity equals 0, where the 0 is identified with the center of synchronization. So mechanically, if we think in terms of mechanics, the center of synchronization plays the role of a fulcrum, according to the notion of Archimedes, or equivalently, a center of mass. So the center of synchronization is a center of mass of all the roots of unity distributed uniformly around the circle. Now let's think from this perspective about the imaginary unit. We already know the imaginary unit corresponds to an imaginary rotation by a right angle. So the imaginary unit to the 4th power, 4 right angles, gives a complete circulation once around the unit circle. In this way, the imaginary unit is qualified as the 4th root of unity. Think of the roots as what you have on the unit circle, so as faces, where faces are complex numbers characterized by a unit radius and the corresponding angle modulo the multivalency of this angle, as those elements which neutralize the corresponding powers, which are expressed algebraically as the degrees of these polynomials of the form w to the nth power equal the unity. So the imaginary unit, and of course the conjugate of it, are the fourth roots of unity. So they satisfy j to the fourth power equals the unity. So here we see how we proceed. We start from the first root of unity, which is clearly only the one. The second root of unity, which is the minus 1. So we have two roots, the 1 and the minus 1. Third roots of unity, fourth roots of unity, where we have the appearance of the imaginary unit and the complex conjugate, and so on. In this way, we identify now the points on the unit circle, the faces, in terms of the roots of unity. So as solutions now of the corresponding polynomial equations by the fundamental theorem of algebra. Now, each root of this unity, since the radius is always 1, is the unit circle, will be described in terms of a face, which will be a face pertaining to an angle, always. And this angle is always measured in radians. This means that each angle is measured in terms of pi. So all the roots of unity now are expressed in terms of the real constant pi. And this is how the pi, together with the universal equation of ciphers, which pertains basically to the windings, makes the tuning according to the equally tempered scale. And this scale now is equally tempered. Why? Because the spacing between the roots is uniform. Or you can think in terms of the corresponding areas. The areas here are equal. So you have, by the roots of unity, a uniform objective probability distribution, the values of which are roots expressed in terms of the exponential function on the circle as faces, which are tuned together in terms of the constant pi. So from the perspective now of the harmonic domain, if we think of each root of unity corresponding to a whole, so to a global thing which is not fragmented into parts, the unit circle on the complex domain gives rise to what we have called a symphony cycle. It is a symphony cycle because it synchronizes, it coordinates together all the roots corresponding to the solution of a polynomial equation of some degree. So in the case, for example, of, let's say, the fourth roots of unity, here you have the 1, here you have the imaginary unit, here you have the minus 1, here you have the conjugate of the imaginary unit, which is the same as minus the imaginary unit. And these now are equally and uniformly distributed around the synchronization center. So the areas here are equal, and they are tuned together. They are tuned together by the constant pi. You see here that as we proceed from the first root of unity, we mark with the color blue some roots. Why we choose this way of indexing our roots? So if we start here, the first root of unity, the 1, appears for the first time. But the 1, of course, is also a second root of unity. But it has already appeared here before. So we already know, we have the memory of this. And we mark the new root of unity which appears. Here we have the third root of unity, solutions of the polynomial equation w a complex number, to the third power equal the unity. 3 roots equally distributed around the unit circle, brought together into a symphony cycle uniformly, but the first root of unity has already appeared at the first stage. So we have to mark now these roots which appear for the first time. And the roots which appear for the first time in this sequence of unfolding according to the roots, we call the primitive roots of unity. The idea is that when a primitive root appears for the first time, so there is no memory of it imprinted from previous stages, we have a novel phenomenon which takes place. This is how we will interpret the notion of primitive roots. You see here, as we unfold in this sequence, that there are cases where almost all, with the exception of the first root of unity, appear for the first time. So, in this way, in the geometric domain, a novel form, geometric form, makes its appearance. Now there is a way to think of the roots of unity geometrically in terms of polygons which are inscribed inside the unit circle. So let's consider the case of the fifth roots of unity here. You see it here that we have 4 primitive roots, and of course the one which is always a root of unity, the tautological root of unity. Now we can consider that there is a line which connects all the roots of unity together. So each root of unity is connected with the next one with a line. In this way, we obtain a polygon. And the polygon that we obtain in this case is, as you can see, it will have 1, 2, 3, 4, 5 sides. This polygon is the pentagon. And the pentagon, you see that it has 4 primitive roots of unity. So everything, with the exception of the tautological one, appears for the first time. In the geometric way now, the pentagon has properties, has peculiar properties, which are understood through the tuning parameter pi, which appear for the first time. You cannot see these properties in the case of the square or in the case of the triangle. And this is a way now to think of how what we call the Platonic polyhedra are geometrically manifesting, because the Platonic polyhedra can be considered in terms of their geometric entities, then be considered in terms of the part-whole relation. So we either triangulated each one of them, but there is the dodecahedron, about which we will talk in the sequel, which is built out of pentagons, which involve the fifth root of unity. And you see that here, the fact that these roots are all primitive, with the exception, of course, of the tautological root, give some unique property to the dodecahedron, which you will not find in the case of, for example, the octahedron or the cube, which is made out of squares and so on. This is just a simple observation to keep in mind and to think of the relation of polygons which are obtained through synchronization via the roots of unity, this notion that we have explained, as building blocks, so as parts, in the wholes, which are, in the geometric case, the Platonic polyhedra. Okay, so we have reached the point now where we can make a perfect sense of what the equally tempered canon is about. Now we are able to grasp through the technology that we have built up to this point completely what is this thing that we call the chromatic scale or the equally tempered scale. Recall that this scale on which we compose music is based on the idea of resolving the incommensurability, the obstacle of the harmonic scale. A thing that we have already talked about in our previous lectures. So we can think the setup now of the equally tempered scale that takes place according to the roots of unity. Which roots of unity? The 12 roots of unity. Since the equally tempered scale is based on the 12 semitones, what we need is to identify each point here. Let's think of it as the unit circle on our complex screen. So the complex plane, but thought as a screen according to our perspective, through which natural communication between harmonics and geometry takes place. So this canon here equally distributes the obstacle, so all the invariance, which is included in the undisclosed center of synchronization, which we have identified with the incommensurability caused by the Pythagorean comma. So these points here are the faces on the unit circle, which constitute the 12 roots of unity. The corresponding sectors of the unit circle is characterized by some geometric area. Now this area, of course, it is characterized it is a positive real number, so it is characterized logarithmically in terms of a color. So the color is a value of the logarithm. But we have to pay attention to the fact that we have identified areas in terms of colors, thinking about areas as areas under the hyperbola. So there should be a transformation from the circle to the hyperbola. This is something that we have to keep in mind, and we will examine in more detail later, in later lectures. But it's good to keep also in mind that if you think of the gnomon and the shadow of the gnomon, then, as we have already discussed in the case of Thales' theorem, if we consider the shadow of the sun during a whole day, so we get a semicircular path, the shadow of it will be a hyperbola. So this is a way to qualify the areas of the sectors of this disk bounded by the circle in terms of areas under the hyperbola, which is formed by the shadow of the gnomon. So this very subtle interplay between the harmonic and the geometric domain appears in many different instances, but we have to think of it, to grasp it, in terms of the communication between these two domains. Let's try to see now, in summary, what this communication between the geometric and harmonic domain amounts to in terms of the exponential and the logarithmic bridge, because we have justified the extension from the real domain to the complex number domain as an extension which takes place through the exponential function from the real line to the circle. In this way, it becomes a bridge between two different structural domains, because the real numbers have some algebraic structure as an additive group, and the circle has also some group structure in terms of multiplication of faces. So, how we proceed to make sense of what this diagram talks about? The idea is that, for example, for the case of solutions of algebraic equations, we have equations of the form x squared equal minus 1, which cannot be solved in the real numbers. So the solution to these equations corresponding to geometrical problems require the extension from the real number domain to the complex number domain, and in particular to the circle. So we need an encoding bridge to do this job. This encoding bridge is an exponential bridge. Is what we have called before the extension of the exponential function from the reals, and in particular the positive non-zero real numbers, to the circle. Since this extension takes place in terms of the imaginary unit, we call it an imaginary exponential bridge. What this imaginary exponential bridge encodes? It encodes the potentiation of angles as faces on the unit circle. So what we do is potentiate now angles, and the potentiation of angles has some particular peculiar property which does not appear in the potentiation of real powers. As we have explained, this potentiation pertains to the multivalency of the angle. The multivalency of the angle, geometrically, is what is at stake, which leads to the windings, to the thinking about the frequencies in the harmonic domain, to the whole setup of the universal covering of the circle by the helix. All this geometrically can be understood through the multivalency of the angle. So what the exponential bridge is doing, it is potentiating angles in terms of imaginary rotations. Now the potentiated angles, they are faces on the unit circle. They are the coordinates of the points of the unit circle. With this bridge, now, we are able to solve any polynomial equation. So we are able to find all the roots of every polynomial equation, the fundamental theorem of algebra. In the case of polynomial equations, where we have a variable raised to a power n equals the unity, the roots are what we have talked about before, are the roots of unity, which give rise always to an equally tempered scale. Now we have to think of the partition spectrum we get in terms of the imaginary exponential bridge. The partition spectrum gives rise to what we will call quantization. Now, how we think of it, just keep in mind the universal covering of the circle. Let's take the unit circle on the complex domain on our screen in terms of the helix. The helix is structured in terms of a series of discrete stairs. Algebraically, these stairs, they are always countable, so they are integers. They give rise to what we call in algebra a kernel. This is the kernel of the group homomorphism from the real additive group to the circle multiplicative group of faces. In this way, the circle is identified as a quotient of the helix R modulo the discrete stairs. It is precisely this kernel now that gives rise to quantization. Quantization leads to what we have called this idea of homology. If you think in terms of the universal covering helix, what we do is we uplift homologically area from geometry, so from space into time, where time now is expressed in terms of the helix. So it is the homological abduction according to the windings or according to the frequencies, the homological abduction of area from space into time, where time is the universal covering given by the helix. In this way, through this partition spectrum, this is a quantum spectrum, this is a spectrum which is understood in terms of quanta, where each quantum bears a length of 2 pi yacht. It corresponds to an imaginary translation, mechanically, of the center of synchronization along the imaginary axis, which transfers mechanically now the imaginary rotations. It is this subtle relation between areas with respect to translation and rotation, which is encoded, which is enciphered in the Pythagorean theorem, the Pythagorean relation of areas. From this quantum now partition spectrum, expressed in terms of quantum phases, we use a decoding bridge which is expressed in terms of the logarithm function. This is now the complex logarithm function. And what is the peculiar novel thing that we get here is the phenomenon of branching. So there is no unique inverse, a global inverse of the exponential bridge in the complex domain. The logarithm can be defined through branch cutting. So in any branch, we can have an inversion of this bridge, and then these branches can be glued together to give rise to a helicoid in non-singular regions. Okay, so this gluing of different branches gives rise to a helicoid which is bounded by the universal covering of the circle by the helix. And we have also discussed the intricate role that orientation plays in this setting, so that we can understand the bounded portions of this helicoid as self-interfering harmonic waves which qualify the windings in terms of frequencies, harmonic invariants, which are integers of winding around the circle. This is how areas are actualized now in the evaluation of the logarithmic bridge with respect to distinct branches which are glued together. So you are gluing together different quanta, and in this way we get back to the real domain. We get back to the real domain by gluing together branches and actualizing the corresponding areas in terms of color. Now, the crucial point that we have to discuss is a closer look on the architectonic inside-outside distinction. I find this very important, and the utility now of the complex calculus and the bridges between harmonic and geometry allow us to obtain a very precise and very clear grasping of this relation between the inside and the outside. So, if we think qualitatively, our areas, according to the pi tuning, so according to the equally tempered scale, are uniformly, probabilistically distributed around a center of synchronization. This is the undisclosed geometrically center of synchronization. The fact now that this center of synchronization is undisclosed is expressed through circulation in terms of this notion in complex calculus, which is called a residue. Now, the idea of a residue is that it is a way to qualify through our pi tuning, taken together, of course, with the imaginary unit, because this is how we consider phases, the undisclosed center of synchronization. So, if we consider the integration of what is included here inside this loop, which is enclosing the center of synchronization, would be equal to the length of one quantum. So 2 pi times the imaginary unit, if we think of a single circulation around this center. Now, in order to make sense of the length of this quantum here, what is called the qualification of this residue in integral terms, we have to see the topological difference between simple connectivity again and multiple connectivity. So a center of synchronization brings forward the issue of multiple connectivity. But if we consider now a region outside this loop, an arbitrary region which does not enclose the center of synchronization, and we consider the integral over this loop not enclosing any center of synchronization, so there is no pole here, there is no singularity, everything is simply connected. So if I consider the integral of a function, a continuous function, on complex numbers, along this circuit here, then since there is no center of synchronization, this integration will be, of course, 0. Think, as a way of visualizing it, what we have said before about the roots of unity, the equal distribution of the roots of unity. But now we have the instance of distinction between the inside, where the inside is what is enclosed within this circuit, which is organized with respect to a center of synchronization. And this circuit here, where inside it everything is simply connected, so there is no center of synchronization. Everything is geometrically simply connected. So if I integrate around it, since there is no synchronization, the result of this will be 0. This now gives what is called the criterion of analytic behavior in the complex plane. So a function, a continuous function of a complex variable, is analytic if the integration of this function, which takes place by circulation around a region which does not enclose any singularity or pole, any center of synchronization, is 0. So let's consider a complex variable here, which we'll call simply z. We want to qualify now the inside-outside distinction. Let's call inside what is included in a region which enclosing a center of synchronization, for example, a pole or a singularity. The integration now in this region of a complex variable z, which is outside, will be expressed as the integral over this circuit of what? Of the reciprocal of z. So, if z is in the outside region, the complex variable in the outside region does not enclosing any pole, any center of synchronization. What lives inside a circuit which is enclosing the center of synchronization will be the inversion, which is expressed as the reciprocal of the complex variable z. So the integral now of the reciprocal of z is the integral of the increment over the reciprocal of z, and this is, of course, the differential of the complex logarithm. So we have the integral of the differential of the complex logarithm. The integral and the differential, they cancel out, and what we have is the primitive, the logarithm, evaluated between the phases that this circuit runs from its beginning to its end. The integration now of the reciprocal, so the values of the complex logarithm from the beginning to the end, taking into account all the windings of this circuit, will give us the quantum length 2 pi times yacht, which corresponds to a circuit circulating once around the center of synchronization times the winding number. This is the fundamental theorem of complex analysis, known as the theorem of Cauchy. But now we got a very simple abductive proof of this theorem, which comes from the distinction, the architectonic distinction between the inside and the outside. A further step is the following. If I consider an arbitrary circuit which is outside the center of synchronization, so everything is simply connected in the complex domain here. Since everything is simply connected, any type of this region being on the outside can be contracted within the unit disk on the outside. So every simply connected region, if I consider complex integration of an analytic function, will give again 0. So I can contract homotopically, since everything is contracted, any region to the region which is bounded by this circuit here outside. So inside the outside unit disk. So the distinction now between inside and outside is the synchronization which can take place between a circuit which is enclosing the center of synchronization and a circuit which does not enclosing it. How this synchronization takes place? This is the question. Here, for one more time, we see what it means for a region to be simply connected. You will see that what it means is that complex integration around any loop in this region here, in the region of this annulus here, since this region is simply connected, will give the same result, will give 0. This annulus here does not enclose any center of synchronization. In this way, there is no residue, which becomes quantifiable in quantum space. So in terms of quanta, in terms of the 2 pi yacht length factor. But in the case of two different loops, D and C, let's think that this loop D is winding once around the center of synchronization. So, again, if I consider a complex variable Z outside, inside we have the inversion, so how it is reflected within this circular mirror, this complex variable, this will be the reciprocal. Integration of the reciprocal around this loop is the integration of the differential of the complex logarithm by the definition of the complex logarithm. So what we get is a residue which gives the length of one quantum, 2 pi yacht. And since this loop is winding one time around it, the winding number is 1. So integration gives 2 pi yacht. This loop here, we can think of it that it is winding around 2 times around the center of synchronization. So, since it is enclosing the pole, the center of synchronization, will also give the same residue, 2 pi times yacht, but now multiplied by the winding number. This is how we distinguish homologically these loops. If this loop is winding 2 times around the center of synchronization, belongs to a different block of our partition spectrum in relation to this one, which is winding 1 time around the center of synchronization. So the integration will give 2 times the residue which is given by the circulation once that we perform along the circuit. But take into account, that is a crucial thing, that we consider as the function that we integrate, so the function that completely specifies how our complex screen behaves is the complex logarithm function. Because we consider, again, an outside complex variable z, so belonging to a simply connected disk here in the complex plane, and we reciprocate this complex variable, so we get the reciprocal 1 over z, which has to be integrated along the circuit. And always remember that if we have dz over z, which is the reciprocal of z, reciprocal of z is 1 over z, so you have the increment dz over z, this is the differential of the logarithm. And the differential cancels the integral, so what you count in terms of the complex logarithm is precisely the residue, which is the way to qualify the undisclosed centers in terms of the tuning parameter pi times the winding number. We still have to see how the inside synchronizes with the outside. Here is where the aspect of orientation, the double orientability, pops in. So in terms of orientation, a loop which is enclosing the center of synchronization is oriented, for example, anticlockwise. Then any other circuit, any other loop on the complex plane which is not enclosing the center of synchronization has to be oriented in the opposite manner. So it has to be oriented, in this case, clockwise. And this is how we distinguish the inside from the outside. Having made this distinction now in terms of orientability, it is possible to think of their possible gluing. And this is what we will perform now. What we see is that the gluing of the inside enclosing the center of synchronization and the outside, which is not enclosing it and being oriented in the opposite way, takes place in an antipodal manner. What this means is that this face here on this circuit, let's call it the circuit which is enclosing the inside, has to be glued together antipodally, so anti-diametrically, with a face on the outside circle, because this circle is not enclosing the center. And this is how it's possible now to obtain a gluing of these two disks together along this composite circuit. And thus you will figure out this composite circuit now is what is enclosing and bounds a Möbius band, which is non-orientable. So the antipodal gluing gives rise to what we have seen on the shadow domain as a shadow of the helicoid, of the helical standing wave, what we have seen as a shadow, this figure 8. Now, with the technology we have on our screen, endowed with a complex structure, which is conscious of the architectonic inside-outside distinction taking place in terms of reciprocation, it's possible to glue this circuit enclosing the inside, enclosing the center of synchronization, with a circuit outside which is not enclosing it. And the only way to glue these two disks together is through antipodal identification. This antipodal identification gives rise to this figure 8 pattern, which is the boundary of a Möbius band. So the Möbius band is not again a geometric object that we can play with in space. It emerges from the architectonic inside-outside distinction and its qualification of it in terms of the two distinct orientations pertaining to the manner that we went around, as well as the positioning of the center of synchronization. In this way, this boundary here that the ancients had figured out, and they have called it the analemma. This figure 8 is what they were calling the analemma, and in what plays the role of a boundary of a Möbius strip is what emerges from the architectonic distinction between the inside and the outside. You see that this is a binary distinction, and it has to be considered together with the homological abduction of area from space. So the homological abduction can take place with respect to the location of a center of synchronization, bearing always within it the distinction, the binary distinction between inside and outside. And this always gives rise to a boundary which has the form of the analemma. And this is what we get through the natural communication as a qualification of this distinction between inside and outside, using now the technology of the complex calculus.